This week, we will use the concepts of momentum and energy to examine an application of great importance, collisions. A collision is an event where two or more objects exert forces on each other over a short time interval and where the interaction forces dominate over any external forces. Common examples are collisions involving projectiles, collisions of motor vehicles, collisions in sports, and collisions between atomic or subatomic particles. It is worth noting that the colliding objects need not actually touch each other in the collision, as long as the interaction force does not require contact. For example, two positively charged protons shot towards each other will repel each other due to the Coulomb electric force. Their interaction can be treated as a collision, even if they never actually touch. We will see that momentum is always conserved in a collision as long as external forces can be entirely neglected. However, energy is not necessarily conserved. This leads to the distinction between elastic collisions, where energy is conserved, and inelastic collisions, where energy is not conserved. We will also derive a simple but powerful principle in the case of elastic collisions in one dimension, that the relative velocity of one particle with respect to the other is simply reversed by the collision.
Let's consider our one-dimensional collision again. Object 1 moving with velocity v1 initial, and object 2 moving with v2 initial. Let's call this our I-hat direction. And this is our initial state. And our final state, after the collision, we have object 1. We'll say it's moving this way, v1 final, and object 2 moving that way, v2 final. Now, recall our principle of impulse and momentum. We said that if there's an external force during the time of a collision delta t, then physically that will cause the momentum of the system final minus the momentum of the system initial. Now, when we do this analysis, this side was a description, and this side is physics. Now, for our one-dimensional collision, we need to look at this collision and ask ourselves, are there any external forces acting on the system, which is consisting of particle 1 and particle 2? So what we're going to identify here is that this surface is frictionless and will ignore all air resistance. And so by our assumptions that there are no F external is 0, and therefore the momentum of the system remains constant. So here our statement is, many people call this conservation of momentum, but we're saying in this example, based on our assumptions, that the momentum of the system is constant. Now, how do we actually write that down? Well, let's now write it first as vector expressions. So we have the initial momentum, v1 of the system, m1, m2, v2 initial, is equal to the final momentum of the system, v1 final plus m2, v2 final. Now, how do we represent these equations? Well, you could treat them as vectors if you wanted, but what we're going to do is express them as components. So if we wrote this as components, we would have m1 be x initial I hat plus m2 be 2x initial I hat equals m1 v1 x final I hat plus m2 v2 x final I hat. So that's the vector expression expressed in terms of components. The advantage of this is that we really don't know the signs of these two final components. That's our target quantities. But we could just write this equation, instead of writing it as a vector equation, let's just now write this as a component equation. And when we write this equation in terms of components, we have m1 v1x initial plus m2 v2x initial equals m1 v1x final plus m2 v2x final. And this equation here is the equation that we'll use to express the constancy of the momentum of the system. We'll call this equation 1. Now, our next approach is to ask, are there any other quantities in this system which are constant? So we analyzed our one-dimensional collision, where we had an object 1 moving with some initial velocity, object 2 also moving with some initial velocity. And after the collision, we just arbitrarily said object 1 is moving this way, and object 2 was moving that way, and we called that our I-hat direction. In this collision, we assumed that it was a frictionless surface, and there were no external forces, so momentum was constant. Now, what about energy? Well, we know that if there's no external forces, then in principle, there could be no external work. However, during the collision, we've established different types of collisions. We said elastic collision is when we are assuming that the kinetic energy of the system, that's K system final minus K system initial, is 0. The statement that the kinetic energy is constant. We have an inelastic collision in which delta K system has decreased. And that can come from some deformation of the objects during the collision. Heat is generated, some sound, some other source of energy, in which energy is always constant, but the kinetic energy of the system could diminish. And we also talked about a super-elastic collision. And in this type of collision, the kinetic energy of the system has increased. Now, that's a little bit tricky in terms of what we're calling our system. But imagine that when these two objects collided, there was some type of chemicals on it that exploded. And so that there was some chemical energy that was converted into excessive extra kinetic energy. So in order to make a model of our problem, we have to beforehand make some assumptions about the nature of the collision. Now, for our particular collision, let's assume that the collision is elastic. So we have two conservation principles. We have that the kinetic energy of the system is constant, and we've already said that because there's no external forces, the momentum of the system is constant. So now we can write down our kinetic energy condition. We have m1, v1. Now here, this can be a little bit tricky how we're going to write this, because remember, kinetic energy is a magnitude squared plus 1/2 m2 v2 initial squared equals 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. Now, because a component, although it can be positive or negative, in one dimension, if you square the component, you get the magnitude. So I can also write this equation, and I'm going to divide through by the halves, cancel all those, as 1x initial squared equal to the magnitude squared plus m2 v2x initial squared equals m1 v1x final squared plus 1/2 m2 v2x final squared. And we've already canceled all the halves, so we have no half there. Now, given this equation, we'll call this equation 1. We can also have our momentum equation, which I'm going to write down as 2 m1 vx initial plus m2 v2x initial equals m1 v1x final plus m2 v2x final, reminding us of our condition of the constancy of momentum. So now, if you look at this, if we're given the masses, all the MIs, and we're also given the initial state of the system, v2x initial, then we have two equations and two unknowns, and we can solve algebraically for v1x final and v2x final. And by determining out the signs of these components, we can figure out the actual final state of the system. So this is going to end up involving a quadratic equation.